Okay, I'm going to start today with a review of what we took up last Thursday, but through an exercise. So I'm going to ask you to please spend the next 10 minutes or so trying to answer these two questions. And if you have an answer, can you please post it in our chat box? So paki-post na lang sa chat box natin kung meron kayong sagot. No? Pwede nyo muna i-post yung sagot nyo sa A tapos post nyo yung sagot nyo sa B, no? Kung gusto nyo, no? For example, if you're stuck doing B, you can already post your answer in A. Okay? So 10 minutes starting now. Okay, I've already received some answers to letter A, a couple of answers. Wala pa rin nakakasagot sa B. Hopefully, you will come up with an answer to B soon. Okay, like I said, you may approximate your answer to B. You may approximate your answer to B. Three more minutes. Okay, 1 minute. 1 minute. Good. Now I'm seeing some answers. Okay, that's it. Ano? Let's discuss. Let me just peep at what your final answers look like. Okay. Okay. Yeah. Some of you have it, right? No? Okay. Okay, good. No? Okay, so let's just discuss the solution to this problem. Okay. So my starting point is I have a p-type semiconductor in thermal equilibrium at room temperature. So room temperature, ibig sabihin yan, sorry. Room temperature, that means this is 300 degrees Kelvin. No? Okay, I have a whole concentration of 10 to the 15 holes per centimeter cube. No? So anong ibig sabihin nito? Whole concentration, that means P is equal to 10 to the 15 holes per centimeter cubed. So the first question is, what is the concentration of conduction electrons? I could have asked the question, what is the concentration of electrons? No? So if I say, what is the concentration of electrons? Alam na nyo, I mean conduction electrons. Pero sa ngayon, linagay ko pa rin conduction electrons. So the question is, ito letter A, ano? What is N? What is N? What formula can I use to solve for N? Anyone? Just shout it out. What formula can I use to solve for N?
NP equals NI squared.
That's right, ano? That's the mass action law. We know that by mass action law, you have NP is equal to NI squared, which means that N is just NI squared over P. What is NI squared? No, what is NI? NI is 1.5 times 10 to the 10. So NI squared is 2.25 times 10 to the 20. You divide this by P, which is given, 10 to the 15. So finally, what is the value of N? No? N will just be 2.25 times 10 to the 5. Okay. What is this? Electrons per centimeter cube. No? So some of you answered 225,000, which is the same. 225,000 electrons per centimeter cube. I think a good number of you got that right. Any question with regard to this? Okay, certain things I want to point out. No? Anong value ng Ni natin? No? Ni is equal to 1.5 times 10 to the 10. Okay? This is per centimeter cubed. What is N? 2.25 times 10 to the 5. If we compare N to Ni, you notice that N is very much less than Ni. No? N is very much less than Ni. Kapag intrinsic, ito yung concentration. Doped, ito yung naging concentration. Bakit ito lumiit? Lumiit ito dahil lumaki yung P natin. Lumaki yung P natin dahil nagkaroon tayo ng donor impurities. Ano? Nagkaroon tayo ng donor impurities, lumaki yung P, and as a consequence, liliit yung N because of the mass action law. So that's the first thing that I want to remind you about. Okay, for this particular semiconductor, what do you think the value of Na is? What is Na? No? And let's assume Nd is equal to 0. Right? Because if Nd were not equal to 0, I can still come up with a p-type semiconductor with this concentration. But let's assume that Nd is equal to 0. What is the value of Na? Anyone? Use your intuition. Or you can make an approximation. If you were to make an approximation, ano value ng NA? Anyone?
Or more approximately 10 to the 15. Meaning,
Exactly. Yeah. Bakit? Bakit? Tama yung sagot, ano? Why is it approximately 10 to the 15?
ano sir, assuming charge neutrality.
Yeah, that's true. You can show that using charge neutrality. Pero well, the answer I was looking for is each of this, you have ano, no? You have this number of holes per centimeter cubed, no? And this is very much larger than Ni. Okay? So you assume that each of this came from an acceptor impurity, no? And therefore Na will be approximately equal to P. Right? So this is equal to 10 to the 15. But you can also solve this using charge neutrality. Pwede rin i-solve to using charge neutrality, no? So, solving for Na using charge neutrality, no? And assuming Nd is equal to 0, ano yung formula natin? N plus Na is equal to P plus Nd. No? Yung N, kinompute na natin. Ano yung N? 2.25 times 10 to the 5. No? 2.25 times 10 to the 5. Yung Na, hindi natin alam. Yun nga ang gusto natin malaman. No? Plus Na, yung P is given. 10 to the 15. Yung Nd, in-assume natin na 0. So, you can now compute for Na. Na is equal to 10 to the 15 minus 2.25 times 10 to the 5. Ang sabi ng calculator ko, 9.999999998 times 10 to the 14. So for all intents and purposes, this is approximately equal to 10 to the 15. No? Okay, which intuitively makes sense, no? Because each of these impurity acceptor impurities will contribute a whole. And the number of intrinsic impurities is much smaller than this. So nagiging negligible yung number of intrinsic impurities compared to this. And that is why, no, if we recognize this, we can just say that P, your whole concentration, is approximately equal to your acceptor ion concentration if there is total ionization. P is just approximately equal to Na. Now, if you wanted to solve it exactly, what did I get? 9.999999998 times 10 to the 14. Sometimes your calculator cannot even distinguish the difference. Okay. Any questions? By the way, I did not ask this in the problem. No? Ang hiningi ko lang is N. No? I just wanted to compute for Na because we can use this sa letter B. No? We can use this letter B. So letter B. What concentration of donor impurities must be added to the sample to convert it to an N-type semiconductor whose electron concentration is equal to the previous hole concentration? So ano yung scenario natin dito? Meron tayong P-type. No? Ito yung hole concentration, 10 to the 15. Gusto ko siyang maging N-type na yung electron concentration is 10 to the 15. No? It is a P-type whose whole concentration is 10 to the 15. Gusto ko siyang maging N-type whose electron concentration is 10 to the 15. In other words, parang nag-sex change siya, no? Mula lalaki, ginawa mong babae, no? From 10 to the 15, let's say yun yung testosterone niya dati, 10 to the 15 ngayon yung estrogen ngayon, no? Something like that, no? If you get the analogy. Okay. Intuitively, what is going to be the value of ND? No? Intuitively, ano yung value ng ND? So intuitively, I need 10 to the 15, okay, donor impurities to make my semiconductor look intrinsic again, no? Look intrinsic. You understand what I'm saying? Kasi meron ka to start with, meron kang 10 to the 15 acceptor impurities. No? Kung gusto ko siya maging intrinsic uli, dadagdagan ko siya ng 10 to the 15 donor impurities. Ano mangyayari, no? For every acceptor impurity, nagkaroon ka ng donor impurity, the two will cancel each other out and it will look intrinsic. Pero hindi yun ang gusto ko. Ang gusto ko, maging N-type siya, no? With N equal to 10 to the 15. No? So, to make it an N-type with N equal to 10 to the 15, I need to add another 10 to the 15 donor impurities. Okay? So, in effect, ano yung ND na kailangan ko? 2 times 10 to the 15. No? Impurities per centimeter cube. Any question with regard to that?
Sir, paano po nakuha yung units?
What do you mean the units?
Like per centimeter cube.
Oh, well, yeah, yung concentration natin is assumed to be per centimeter cube. Our concentration is always number of carriers or number of impurities per unit volume or per centimeter cube. So lahat itong mga to, yan, 10 to the 15 volts per centimeter cube, no? This is 2.25 times 10 to the 5 electrons per centimeter cube. All of these are per centimeter cube. Was I able to answer your question? No. Naintindihan ba nyo what I was trying to explain dito sa B? Yung unang 10 to the 15, yan yung pang-neutralize ng initial number of acceptor impurities. Yung pangalawang 10 to the 15 is to make it now an N-type whose N is equal to 10 to the 15. Did you understand that? Okay, good, no? I hope, no? I hope. Now let's say you didn't want to do it intuitively. Let's say you wanted to do it using formula, no? Okay, by formula, so this is intuitive, no? So by formula, N plus NA is equal to P plus ND. Yung NA, alam na natin yan from this problem, ano? From the previous letter. NA is equal to 10 to the 15. No? By the way, yung N natin is 10 to the 15. So this is 10 to the 15. Ang NA natin is also 10 to the 15. Ang P natin, well, we haven't computed for P. Magbabago yung P. When we dope this now with donor impurities, magbabago yung P. But you can get P. P is just Ni squared over N. No? okay, by mass action law, plus ND. Ito yung unknown natin, ND, unknown. Okay, Ni squared over N, we already know that to be 2.25 times 10 to the 5. No? So finally, you're going to get ND is 10 to the 15 plus 10 to the 15 plus minus 2.25, sorry, minus minus, no? Ito minus 2.25 times 10 to the 5, and this is approximately equal to 2 times 10 to the 15. So let's say you're insecure about doing an approximation, then you could have always used the formula. Any question? So I hope you become very comfortable doing these types of calculations, ano? Given a desired electron or hole concentration, paano ba natin idodope yan? No? Ilan ang acceptor ions na ilalagay natin or ilan yung donor ions na ilalagay natin? And if we end up with this electron concentration, ano yung magiging hole concentration? So those things, you should become quite comfortable making those types of calculations. Okay? Okay? Okay, so if you don't have any questions, I'm going to go to what I prepared for you for today. Actually, the lecture that I will start today is meant for 2 lecture sessions. So we'll hopefully be able to complete half of it now and then go through the next half next Thursday. No? Hopefully sa Thursday kita-kita na tayo, no? Hindi via Zoom. Okay. Sorry, just adjusting my screen. No? Okay, so this is what we're going to take up in this second part of topic 1, Fermi function, conduction mechanisms in semiconductors. So these are what is going to be covered. We're going to take up the Fermi function. I hope you don't get intimidated by this. This is a mathematical formula. The concept is a little bit, how do you say it? It's a little bit theoretical, no? But I'm going to try to put it in very simple terms. Okay. And then we're going to take a look at carrier concentrations. And then finally, we're going to take a look at conduction mechanisms. So that is what is going to be covered by these next 2 lectures. So let me start with the Fermi function. Each energy level in an energy band diagram has a certain probability of being occupied by an electron. Let me repeat that. No? Each energy level in the energy band diagram of a semiconductor has a certain probability of being occupied by an electron. Now, the Fermi function, sometimes called the Fermi-Dirac function, can be used to compute this probability. And what does that function look like? This is what that function looks like. So this is the Fermi function. Okay. This is the energy level of interest. E is the energy level of interest. And we say that the probability, or f of E, is equal to 1 over 1 plus E raised to the E minus EF divided by KT. This is the Fermi function. So E is the energy level of interest. E of F, we call that our Fermi energy or Fermi level. So this is dependent on many things: doping level, material, temperature. Okay, that is the Fermi energy level. K is called Boltzmann's constant. If you take a look at Boltzmann's constant, 8.62 times 10 to the minus 5 electron volts per degree Kelvin. Electron volts is a unit of energy. EV is a unit of energy. So this is energy per degree Kelvin. So this is like a conversion between energy and temperature, no? And temperature in degrees Kelvin. Okay, note that at E equal to EF, f of E is equal to 1/2. At E equal to EF, this is e to the 0, e to the 0 is 1, f of E is equal to 1/2. So E of F is the energy level that has a 50% chance of being occupied by an electron. Energy level that has a 50% chance of being occupied by an electron. And in a system that is in thermal equilibrium, there's only one value of E where that is possible. No? So there's only one Fermi level. There's only one value of E whose probability that it is occupied by an electron is 50%. And that is the Fermi level. Let us consider an intrinsic semiconductor. Ano yung ibig sabihin ng intrinsic? Pure semiconductor. Okay? This is your energy band diagram. And I converted the horizontal axis into our Fermi function. So this is the probability. This is the probability that that energy level will be occupied. And this is the energy level. The graph of energy level versus probability. I want to take a look at what this will look like at 0 degrees Kelvin. No? Let's take a look at what this will look like at 0 degrees Kelvin. At 0 degrees Kelvin, okay, E raised to the E minus EF over KT, this will be either plus infinity or 0, no? Or 0. At 0 degrees Kelvin, E raised to the E minus EF over KT is going to be either equal to plus infinity or 0. When will it be equal to plus infinity? May I hear from you? Kailan niya magiging equal to plus infinity?
When E is greater than E.
That's right, ano? This is when E is greater than EF. And when will that equal to 0? No? When E is less than EF. Right? Kung E mas malaki sa EF, kahit nakatiting lang, ano? Kahit nakatiting lang, kung itong E mas malaki rito, this will be equal to infinity, and therefore E to the infinity is equal to infinity. When E is less than EF, okay, this will be equal to minus infinity. When E is equal to EF, this will be equal to minus infinity. What is E to the minus infinity? It is equal to 0. So, in this particular case, f of E is going to be equal to 1. Is going to be equal to 0. No? If this is infinity, 1 over infinity is 0. And in this particular case, f of E is going to be equal to 1. No? If this is equal to 0, 1 over 1 is equal to 1. What will the graph look like? No? What will be the graph of the Fermi function? It's going to look like this. Okay? When E, ito yung EF natin, okay, I'm just assuming EF is somewhere between EC and EV. No? Ito yung EF natin. When E is greater than EF, what is my probability? 0. When E is less than EF, what is my probability? My probability is 1. Okay? So when E is less than EF, my probability is 1. When E is greater than EF, my probability is 0. Okay. Where do we have energy states? We have energy states here, no, in the valence band, and we have energy states here in the conduction band. So notice that all the energy states in the valence band will have a probability that they are occupied, will have a 100% probability that they are occupied. In other words, all valence bands are intact. On the other hand, all energy states in the conduction band will have a zero probability that they are occupied, no? No? Which makes sense. If these are all intact, walang pupunta dito. Okay? So that is what it will look like at 0 degrees. Now let's raise the temperature. Let's raise the temperature, but not that high. So let's assume this is a low temperature. Okay. Ano mangyayari, no? So hindi na 0 yung T, pero maliit. Yung curve natin will end up being an S-shaped curve. So I actually plotted this curve, no? Using a plotting tool. So this is an S-shaped curve. Okay? Notice, no? This is E of F. That is where your probability is equal to 0.5. Now take a look. No? Lahat ng electron states or lahat ng valence bonds dito will still have the probability that they are occupied. No? Will still have a probability of 1. And lahat ng energy states dito will still have the probability of 0, or which will mean that they are not occupied. So there is still no free electrons. This is still acting like an insulator. No, there are no free electrons. All your charge carriers are still bound to your nuclei, no? Essentially. Okay. What will happen at room temperature? At room temperature, okay, the curve becomes less severe, no? It becomes now a more subtle curve. Ano nangyayari? Dito, the probability that your electron exists is already becoming less than 1. If it is less than 1, ibig sabihin meron ng there are already empty covalent bonds here. Dito sa area to, no? The probability is less than 1, there are already empty covalent bonds. Saan pumunta yung electrons na umalis dito? Dito, no? They will occupy now the energy states depicted by this, where the probability that it is occupied is already greater than 0. It is no longer 0. So may probability na. No? So what is this now? These are your intrinsic electrons, and these are your intrinsic holes. Together, or well, they form your intrinsic concentration. Ano? So the number of electrons and the number of holes will be your intrinsic concentration. Now, for intrinsic semiconductors, E of F will always be halfway between EC and EV. And that intuitively, that should be the case. Because for every empty valence bond here, you would have a corresponding electron promoted to your conduction band. And therefore, the 50% probability will be halfway. Any questions so far? Any questions? Okay. If you have any question, please shout out, no? Please shout out. If you just wave your hand or post something in the chat box, baka hindi ko makita, no? Because I'm taking a look at the slide. Okay, just some notes. E of F is the energy level that has a 50% chance of being occupied. However, it is possible for no electron state to exist at E equal to E of F. So that is very much depicted by this, ano? This is very much depicted by this. Okay? At E equal to E of F, sabi natin there's a 50% chance of being occupied. No? Pero kung wala namang energy state dito, wala din siyang pupuntahan. So this is actually a theoretical value of probability. No? It is a theoretical value of probability that is only based on the energy level E. Okay? So f of E specifies the probability, but does not take into consideration the availability of energy states at that energy level. So if you go back to the analogy I made about the stadium, where you have seats that go higher and higher, you might have the energy to go to the middle level. You might have the energy to climb and go to the middle level. Pero kung wala namang upuan doon, hindi ka rin makakaupo. No? And since you don't have more energy to bring you to a higher level, bababa ka rin to the seats that are in the lower level. So that's the analogy that I make. No? So while there is a probability, that is the probability that you could go to the middle level, pag walang upuan, there's nothing to occupy. Any question with regard to that? Okay, let me go back to the intrinsic semiconductor. So this is just a summary of what I already mentioned. This is at 0 degrees Kelvin. This is at low temperature. So here, all valence bonds are intact. Probability of occupancy is 1. Here, all valence bonds are still intact. Probability of occupancy is still 1. But at room temperature, meron ng valence bonds dito na less than 1 na yung probability that they exist. No? In other words, meron ng nakalikas na mga electrons dito, andito na siya sa conduction band. Dito, the probability is no longer 0. It's already greater than 0. So I already mentioned that those are your intrinsic carriers. No? Remember that this is an intrinsic semiconductor. Okay, here are equations that you can use to relate concentration, intrinsic concentration, Fermi level, and intrinsic Fermi level. By the way, I forgot to mention something very important. Ito, no? For intrinsic semiconductors, E of F will be halfway between EC and EV, no? So kapag intrinsic yung semiconductor, E of F, nandito sa gitna ng EC at saka EV. Ang tawag natin dyan, intrinsic Fermi level. So we also call that E of I. Sorry, I forgot to mention that. E of I. Okay. So these are equations that you can use to relate concentration, intrinsic concentration, Fermi level, and intrinsic Fermi level. By having said that, I am implying that sometimes E of F is not equal to E of I. And in fact, that happens when your semiconductor is not intrinsic. Kapag dope na yung semiconductor natin, yung E of F no longer is equal to E of I. Now, we're not going to go through the derivation of these formulas. No, it takes a deeper understanding of semiconductor physics to derive this formula. So I hope you just accept it as is. So how do I compute for my electron concentration? If I know the value of E of F, I can just compute E to the E of F minus E of I over KT. So of course, this is at a specified temperature. You multiply that by your intrinsic concentration. On the other hand, you can get the difference between E of F and E of I using this formula. So this is just computing for E of F minus E of I from this formula. This is for electrons and this is for holes. Notice for electrons, it is E of F minus E of I. For holes, it is E of I minus E of F. Okay, so here's an example. N-type silicon semiconductor. Nd equal to 10 to the 16 impurities per centimeter cubed. Assuming total ionization, nasaan yung E of F? Nasaan yung E of F dito? Okay? We're going to do that at 27 degrees centigrade. So my first question to you, what is the value of N? What is the value of N? What is going to be my electron concentration? Anyone? Anyone?
Sir,
Given, yes,
sir, approximately 10 to the 16.
good, very good. Thank you for answering. No, so n will be approximately equal to 10 to the 16. Bakit? No, because if it is total ionization, so we assume each one of these atoms will contribute a free electron. Eh yung Ni natin is only in the range of 10 to the 5, 10 to the 10, ano? 1.5 times 10 to the 10. So this is 10 to the 5 times greater than Ni. So magiging negligible yung Ni. So N, no, will be approximately equal to N of D, which is 10 to the 16. No? And therefore, magagamit ko na yung formula dito. Itong formula na to. E of F minus EI is KTL and N over Ni. No? So we get E of F minus E of I is 0.35 electron volts. So nasaan yung E of F ko? Ito yung E of F ko ngayon. It is 0.35 electron volts higher than E of I. Where is E of I? E of I is in the middle of EC and EV. And at room temperature, the difference between EC and EV is approximately 1.12 electron volts. Although this is immaterial, this has nothing to do with the solution. No? I just wanted to point this out. No? Na ang EC minus EV is 1.12 electron volts for silicon at room temperature. So yung E of I nasa gitna nun, and yung E of F, sa intrinsic, andito yung E of F, ngayon, dope siya, aakyat yung E of F. So doping a semiconductor with n-type impurities causes the Fermi level to shift up toward the conduction band. What do you think will happen to the Fermi level if we dope it with p-type impurities? Anyone?
Bababa po siya.
Bababa siya, no? Parang leading yung answer ko. Leading yung question ko, no? So it can be similarly shown that if you dope it with a p-type impurity, the Fermi level is going to shift down toward the valence band. Okay, to summarize, ito intrinsic at room temperature. So meron tayong carriers dito, konting N, meron tayong carriers dito, konting P, pero konting-konti lang. Those are your intrinsic carriers. Anong mayayari sa N-type? Yung EF ko, nag-shift up. So itong buong curve na to, mag-shift up yan. No? It will shift up. So this is now my new curve. What happened to the number of holes? No? When this curve shifted up, ano nangyari sa holes? Umunti. Di ba? Now my holes will be less than Ni. What happened to my electrons? This curve shifted up. Uy, dami na ngayon, ano? Because now I have a bigger number of electrons whose probability that it is in this particular space is greater than 1. No? So ito ngayon yung majority carriers ko. Ito ngayon yung minority carriers ko. No? Itong nasa baba. This is now my minority carriers. What will happen to a p-type? Ang p-type naman, this curve shifts down. No? Ang electrons ko rito, uunti compared to my intrinsic. Pero take a look at my holes. Since the curve shifted down, ang dami ko ngayong holes dito. So this is now my majority carriers and this is now my minority carriers. No? So I'm just showing you from a probability standpoint how we end up with more electrons than holes in an n-type and how we end up with more holes and electrons in a p-type. And this is all explained through the Fermi function.
Sir, for the example earlier, yung temperature, do we plug it in Celsius form or in Kelvin?
Yeah, K, it depends on the K, ano? It depends on the units of K. In this particular case, K is electron volts per degree Kelvin. No? So did that answer your question? So dapat
Sir,
Kelvin.
so we need to convert po muna into Kelvin yung temperature.
Yes, what is 27 degrees centigrade? How much is that in Kelvin?
300 something.
Yeah, that's 300, ano? That's 300. So, pag nakita niyo yung 27 degrees centigrade, alam na niyo that that's 300 degrees Kelvin. Okay? Also, 25 degrees centigrade, I think, is 290 degrees Kelvin, something like that. Anyway, no, forget it. No, forget I said that. Yeah, degrees Kelvin. Any other question? Okay, so just to summarize about Fermi function, no, because I'm going to leave Fermi function now, but we're going to refer to the Fermi level many, many more times in the future. To summarize, that's the maximum energy an electron possess at 0 degrees Kelvin. No? Okay, at 0 degrees Kelvin, notice that yan yung pinaka malaking temperature, malaking energy na pwedeng magkaroon ang isang electron. Theoretically. No? Theoretically. Okay? F of E is a probability function. A probability function is from 0 to 1 or from 0 to 100%. Okay? If it is 0, that means it is not possible. If it is 1, that means it is certain. If it's between 0 and 1, then it's possible, but it is not certain. No? Okay, this F of E does not take into consideration the availability of electron states at the energy level of interest. So I already pointed out. If E of F is in the forbidden band, there are no energy states there. No? So even if the probability that that is occupied is 0.5, pag wala namang mapupuntahan yung electron, it cannot go there. So that is F of E, no? F of E shows that at 0 degrees Kelvin, semiconductors act like insulators regardless of whether they are intrinsic or extrinsic. Going back to this, no? Anong mangyayari? So this is intrinsic. Anong mangyayari if this were an N-type? Aakyat lang tong graph na to. Pero it's still going to be 0 here. It's still going to be 1 here. Bababa lang to sa P-type. 0 pa rin rito, 1 pa rin rito. No? So whether intrinsic or extrinsic at 0 degrees, it is like an insulator. And then we showed that for intrinsic carriers, when you raise the temperature, okay, nagkakaroon ng intrinsic carriers sa conduction band at saka sa valence bond. No? And for extrinsic carriers, we showed how majority and minority carriers are formed. And then important is the formula that was provided. Ito. No? This formula that was provided, no? To be able to relate concentration to intrinsic concentration for a particular Fermi energy level, no? At a particular temperature. Okay. Any question again before we leave Fermi function? Okay, I'm now going to go to conduction mechanisms in semiconductors. So we already see that in a semiconductor, there are two types of charge carriers, electrons and holes. No? In intrinsic, exactly the same number of electrons and holes. In extrinsic, depending on N-type or P-type, there will be majority and minority carriers. Okay. Now, this movement of carriers can be attributed to one of three possible mechanisms. The first is drift. The second is diffusion. The third is recombination generation. We're going to take up 1 and 2 in some detail, and we're going to touch on 3. No? We're not going to dwell on 3. No? Just touch on it, just introduce you to the concepts involved here. No? Pero itong 1 and 2, we will take it up in some detail. So umpisahin natin dito sa drift. What is drift? No? Drift is the tendency for charges to move when they experience an electrostatic force. No? And that electrostatic force is normally when an electric field is applied. When an electric field is applied. Now, in physics, no, you know that force is equal to mass times acceleration. So if we're talking about an electron, may version ng equation na yan for electrons, ano? Where mass is what we call the effective mass of an electron, which is an empirical number, and acceleration is the acceleration of that electron in the presence of this force. Okay, in electrostatics, we also know that the force experienced by an electron will be opposite the direction of your electric field. And the force is going to be equal to your charge, negative times your charge times your electric field. Why is this negative? Because the force is opposite the direction of your electric field. Okay, so those are your two equations that dictate, two equations, no, that dictate the movement of your electron, your force that is due to your electric field. Now, this force is going to be superimposed on the scattering motion, on the Earth's-wide scattering motion of charges. Do you remember what we meant by scattering? Can somebody remind me? Anong ibig sabihin ng scattering? Naalala niyo ba? Anyone? Well, when did we talk about scattering? Okay, so let me just try to refresh you. No? At room temperature, if you take a look inside your semiconductor, your charges and your nuclei and your atoms will not be stationary at room temperature. They will be vibrating. No? And if you have charges that are in the conduction band, no, they will be constantly colliding with either other charges in the conduction band or with the nuclei, no, of the lattice atoms, with the nucleus of the lattice atoms. So these are constantly in motion. Now, if there's no electric field, that motion is completely random. No? So there is no net flow of charge. But these charges will be in motion. No. Pag naglagay tayo ng electric field, okay, what will happen? Okay, so let's take into consideration an electron in the presence of an electric field. So this is your electron. This is your electric field. Okay, what will happen? It will experience a force. And the direction of that force will be opposite the direction of your electric field. Kaya nga ito negative, negative Q. No? That force is negative Q times E. By the way, notice that I use this, no, to denote electric field. No? We reserve this to denote energy. So we don't want you to confuse this with this, no? So pag electric field, usually ito yung ginagamit naming symbol, no? So electric field yan, yung capital letter E, we use that to denote energy. Okay, so what will happen? No? So this will experience a force going toward the left. If this were a vacuum, this will just accelerate. Kaya nga mass times acceleration. No? So kung vacuum to, this will accelerate. Ang problema, hindi yan vacuum. That is in a solid. No? may other electrons, and there are also other atoms that form the lattice structure of your crystal. So ang magiging actual movement niya might look something like this. No? Pagdating dito, it will collide with something, it will deflect down here, it might even deflect a little bit backward, but eventually it will go forward again. No? Now notice that there will be a net movement toward the left. No? In fact, it will approach an average velocity toward the left. No? So it will not accelerate, but it will approach an average velocity toward the left. No? So that's what I'm saying here. Due to scattering, electrons will not achieve constant acceleration. Instead, an average drift velocity will be attained opposite the direction of E. So let's take a look at this particular scenario. This is a semiconductor block. I have an electric field. I apply a voltage. So that is what will cause my electric field. By the way, hindi na ito thermal equilibrium, no? Kasi meron ng voltage. So my holes will tend to go to the right. My electrons will tend to go to the left. This is a solid. Because of the electric field, sabi natin, yung electrons at saka yung holes, hindi yan mag-accelerate. It will achieve an average velocity. Now, that average velocity will be proportional to your electric field. No? For holes, the constant of proportionality is called μ of p. And for electrons, the constant of proportionality is called μ of n. No? What is μ of n and μ of p? That is hole mobility and electron mobility. No? What is mobility? It is a measure of how easy it is for the carrier to move. No? So parang gaano kaliksi yung carrier. Gaano kaliksi yung carrier. No? You apply impetus, you apply an excitation. What will its response to that excitation be? Will it be fast or will it be slow? Yun yung mobility. For holes at room temperature, for intrinsic silicon, that's 480 centimeters squared per volt second. Yung V is volt. And for electrons, it's 1,350 centimeters squared per volt second. Notice that electrons are much more mobile than holes. In fact, we say that electrons have 2.5 times the mobility of holes, no? Almost 3 times the mobility of holes. No? Now, why is that so? Well, kasi yung electron, in the presence of an electric field, basta aandar lang siya. No? Whereas yung hole, in the presence of an electric field, for there to be hole drift, that will involve many electrons moving, no, along the hole direction. Remember that holes don't actually flow, it's electrons that flow. And that's why your electrons have a higher mobility than your holes. Now, when you dope a semiconductor, the mobility will decrease somewhat, no? Because your scattering will increase. Okay? But don't worry, we will always give you the value of mobility that you should use. Any question with regard to mobility? Okay, so let's try to derive an expression for drift current. So let's consider drift current due to holes. Drift current due to holes. No? So let's assume that P is the hole concentration. This is my semiconductor material. It has a cross-sectional area of A. My current is flowing in the X direction. Cross-sectional area A. The total number of holes over length X is given by P, hole concentration, multiplied by AX. Take note that AX is equal to A volume. If I multiply A, itong area, by a certain length x, then I am referring to the volume of that particular block. No? So this is actually volume. This is volume. And this is concentration. So if I multiply concentration by volume, I'm going to get my number of holes. Okay. Now, how do I get the total charge? If I know the total number of holes, I multiply that by the charge of an electron, and that will give me my total charge. So this is equal to the total charge due to holes. Remember that the charge of a hole is equal to the charge of an electron. This is the total charge due to holes. How do we define current? Current is charge per unit time, or the derivative of charge per time. No? So current is dq by dt. And what is that? No? That is QPA dx dt. So I just differentiate both sides of this equation. No? dq dt, that's QPA dx dt. No? But what is dx dt? That is just drift velocity. No? So this is just drift velocity. Okay? But what is drift? Sabi natin, drift is equal to mu of p times E. That is our drift velocity. So finally, I get this. No? That is my current along the x due to holes. Due to holes lang to. No? Due to holes. Instead of current, I'm oftentimes more interested in current density. Current density is current per cross-sectional area. No? Current per unit cross-sectional area. So all I have to do is divide both sides of this equation by A. My I becomes J, current density. Mawawala yung A dito. So my current density is QP mu of P times E. That is my whole current density. Whole current density. It can similarly be shown that for electrons, this is my electron current. No? N times A is my volume. QNA is the total number of, NA is the volume. QNA is the total charge. Mu of E is my drift velocity. And then if I get the current density due to electrons, I just have to divide both sides by A. So this is my current density due to electrons. So note, I have current due to holes along the x direction. I have electrons flowing opposite the x direction, no? But that will also contribute current. No? What is the total current going to be? The total current density due to drift will be that due to holes and that due to electrons, which is now Q, no? Factoring out Q, N mu of N plus P mu of P, factoring out again electric field intensity, which we can simplify into sigma times E, where sigma is just Q, is just this, no? Q and mu of N plus P mu of P. This is what we call conductivity. Don't mind this question first, ano? Tignan na lang muna natin to. This is what we call conductivity. Are you familiar with conductivity? Conductivity is the reciprocal of resistivity. No? The reciprocal of resistivity is your conductivity. If you want to get the resistance of the block, I'm sure you learned this equation in the past. Resistance is equal to resistivity multiplied by length divided by cross-sectional area. That's how you compute for resistance. In other words, you should now be able to compute for the resistance of this semiconductor block. No? If you know all of the parameters associated with that semiconductor. What are these parameters that you would have to know? You'd have to know the mobility. You have to know the concentrations of electrons and holes. And you have to know the charge of an electron, which is constant. No? That's 1.6 times 10 to the minus 19 coulombs per electron, or 1 E per electron. No? If 1 E per electron, 1 electron per electron. Okay, now I have a question here. Take a look at this. The holes will be flowing to the right. Electrons will be flowing through the left. Why are these additive? Why do you add these two? No? When one is flowing to the right and the other is flowing to the left. Anyone? Why do you add that two? Okay, I'll let you think about that on your own. No, you should be able to figure that out on your own. Why you add these two when the charges are moving opposite the direction of each other? No, why do the drift currents contribute to each other? Okay, that's actually, well, next I have an example. No, but I'll give you a chance to absorb the material first. I will post these notes in Uble. You might want to study the example in advance. Okay. But we'll take up an example next time, and then next time we will take up diffusion, and then we will take up recombination generation. Any questions?
Sir,
Yes, huh?
kung po sa carrier drift, ano po yung effective mass?
Ah, ah, meron yung it's actually well, we call it an empirical value, no? Parang based on what they observe for a certain semiconductor, no? They can come up with a number that will relate force with basically asan yung ano, no? Ito, no? They can parang ano to parang experimental value yan eh. This is derived experimentally, no? Parang it's just a way of expressing the force in terms of the acceleration that is experienced by the electron, for example, in free space, no? Kasi mahirap talagang makuha yung mass ng electron. I think you will agree with me, no? So parang they just came up with something with a concept called effective mass. But you don't have to worry about that. It's just a concept that they use to relate the acceleration of electron with respect to the electrostatic force that it receives from an electric field.
Thank you, sir.
Yeah. Merong mga published values yan sa mga references. Any other question? Okay, if you don't have any questions, I will clean up my notes, and then I will also publish a link to the lecture so that you can review the lecture also, no? And then hopefully we'll be able to see each other on Thursday. Okay, I will close the session when the last person logs out, so that anyone that wants to stay on to ask me anything in particular can still ask me a question. Okay, that's it. Thank you.
Thank you, sir.
You're welcome.
Thank you po.
Yeah, you're welcome.
Thank you po, sir.
Thank you po, sir.
Yeah, welcome. You're welcome.